All right, so we're going to actually, in a little while, actually on the next slideshow, the second part of this, we're going to continue on with moles and grams. But for right now, we're going to talk a little bit about chemical formulas. So some chemists out there can figure out, or you can take an unknown compound and figure out what is the percent composition of the different elements in it and figure out what the molecule is that you're talking about. This actually is going to go first we're going to start by going the other way. So we're going to talk about the percent composition of a compound. Because when you look at a formula, so like H2O has a 2-to-1 ratio of H to O. Well, now that we know about moles, that's really like a mole to mole ratio. Well, I mean, it could be there's 2 hydrogen atoms for every 1 mole of, 2 hydrogen atoms for every 1 oxygen atom, but we can also say there's 2 moles of hydrogen for every 1 mole of oxygen. So that's a mole to mole ratio. It is not a weight ratio. So percent composition deals more with mass percent, or looking at the different masses of it. So a mass percent of any element in a compound is the mass of that element divided by the total mass of the whole compound. So let's see what that means. All right, so let's do an example. Let's calculate the percent composition, that's the mass percent composition of butane, C4H10. The first thing we need to do is find the molecular mass of C4H10. So we know how to do that. There's 4 carbon atoms. They each weigh 12 grams. So 1 mole has 48 grams. And then there's 10 hydrogen. They each weigh 1 gram per mole. And so 10 hydrogen atoms weighs 10.1 grams. So if we add those together, we get the molecular mass of butane, C4H10. So now we can calculate the percentages. So the percentage is just the mass of one part divided by the whole. So the percent of carbon is just the 48 grams of carbon divided by the total, 58.1 grams, times 100%. So 82.6% of the carbon, 82.6% of butane is carbon. And then to find hydrogen, we can either, since there's only two atoms in this molecule, we can subtract from 100, or we can take the part that's just hydrogen, 10.1, divided by the total, 58.1, and we get 17.4% hydrogen. And again, the total masses should add up to 1. If there were 3 elements, the 3 percentages would have to add up to 1. All right, so now what if we do the opposite? To be able to take the percent compositions and then find out what the formula is. So let's say if you had an unknown, you could figure out the percent composition by doing different types of reactions, and then you can figure out what the formula is. So again, just keep in mind that when you see the mass percent, that has to do with the mass, and the formula has to do with the mole ratio. So we're going to have to, at some point, convert from grams to moles. So the percent composition leads to what is called the empirical formula. So first let's define that. An empirical formula for a compound is the formula of the substance with the smallest whole number subscripts. So in other words, the molecular formula C6H6 would have an empirical formula of CH. The molecular formula C2H2 would also have the empirical formula CH. So the empirical formula is just the lowest ratio. So there can be more than one molecule that has the same empirical formula. N2H4 would have the empirical formula NH2. So if you can divide by some kind of common factor. Okay, so let's find the formula for the compound which, when analyzed, was found to contain the following: 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. All right, so these are not the mass percentages, these are the actual masses. Well, I think we'll do an example with percentages in just a minute. So again, remember that these are mass ratios. There's 13.5 grams of calcium for every 10 grams, 10.8 grams of oxygen for every 0.675 grams of hydrogen. But what we're looking for is the mole ratio. So at some point we're going to have to divide by the atomic weights of these elements. So what we're trying to find is the smallest whole number ratio of the subscripts in this formula. So in other words, we want to know how many calcium to how many oxygen to how many hydrogen. How many, the actual number, not the mass. And because they each have a different mass, we're going to have to factor that out. So what we do is take the grams and convert them to moles. So again, we're looking for the mole ratio, so we take the mass and convert to find moles. So 13.5 grams of calcium, we divide by the molecular weight of calcium, and we get 0.337 moles of calcium. If we take the oxygen, 10.8 grams, divided by its molecular weight, 16.0 grams, we get 0.675 moles of oxygen. And then if we take the hydrogen, 0.675 divided by the molecular weight, 1.01, we get 0.668 moles of hydrogen. Okay, so in a way, we now have our ratios. And you may be able to see the ratio a little better now, but if not, let's take it a little step by step. So it really means this. It means we have calcium 0.337, oxygen 0.675, hydrogen 0.668. Obviously, this is not very good way to present it. We really like the smallest ratio of whole numbers. So some of you may already be able to see that, and with rounding errors and stuff, that the oxygen and hydrogen are about the same and the calcium is about half as much. So it's really like a 1 to 2 to 2 ratio. If you can't see it very well, though, the technique to figure out the whole numbers is to take each number and divide by the smallest. Okay, so in this case, the 0.337 is the smallest. So you take each number. So for calcium, 0.337 divided by 0.337 is 1. And that's, you're always going to get 1, that's a 1. And then you take the 0.675 divided by 0.337, and that gives you approximately 2. And then the 0.668 divided by 0.337 also gives you 2. So you can find the ratio by dividing by the smallest number, and that will give you whole number ratios. Actually, every once in a while you might get, don't round too much. So if you're doing this technique and you get something really close to like 1.5, you're going to have to then do it again and multiply everything by 2 to get rid of the fractions. If you get something that's close to 1 1/3, you might have to multiply everything by 3. But if they come out really close to a whole number, then you can use that whole number. So in fact, this ratio is CaO2H2, Ca1O2H2. So it had the mass ratio, and now we have the mole ratio. This is actually CaOH2 in parentheses is the actual molecule, but the first answer is perfectly fine. So again, what I was saying, don't round too much. If you don't get whole numbers when dividing, you may have to multiply by a factor, and I'm going to show you an example of that right now. All right, so benzoic acid is a white crystalline powder used as a food preservative, and the compound contains 68.8% carbon, 5% hydrogen, and 26.2% oxygen by mass. So these are the mass percentages. What is its empirical formula? So again, when I'm asking for the empirical formula, we're looking for the mole ratio. So we're going to have to take the mass ratio, divide by the molecular or the atomic weight of each element to find the number of moles that are present, and then look at the ratio of the moles to each of them. So again, take now you might say, well, wait a second, in the last example I knew how many grams I had, and I divided by the molecular weight, or the atomic weight. Grams divided by grams times moles gives me moles, and I don't have grams here, I have percentages. Well, it's really the same idea. It's a mass percent ratio. So you could say oh, if I had 100 grams of this, I would have 68.8 grams of carbon, 5 grams of hydrogen, and 26.2 grams of oxygen. You might also say, well, what if I had 1 gram of it? Then it'd be 0.688 0.05 and 0.262. Usually it's easiest, since 100%, it's easiest just to say, well, we'll take 100 grams and figure out. So just consider the percentages the same as grams. So 100 grams, let's say we have 100 grams of benzoic acid, and then we know that we have 68.8 grams of carbon, 5.0 grams of hydrogen, and 26.2 grams of oxygen, which I just said. All right, so now the next thing we do is divide by the atomic weight of each of those. So we convert the masses to moles. 68.8 grams of carbon divided by 12 is 5.73 moles. 5 grams of hydrogen is 5.0 moles. And 26.2 grams of oxygen is 1.64 moles. Again, it might really be hard to see these mole ratios. They're, technically speaking, we could write the formula C 5.73, H 5.0, O 1.64. Now these are not, we want whole numbers. And also notice that in the last example, 0.675 and 0.668 are all pretty close to each other. But 5.73 and 5.0 are not very close to each other, so they're not likely going to be the same number. But let's see what happens. So again, divide by the smallest number to get a different ratio. Don't round. All right. So if we take our carbon, 5.73 divided by 1.64 gives us 3.5. So again, don't round that to 3, don't round that to 4. It's pretty much smack in the middle of 3 and 4, so don't round it. Hydrogen gives us exact 3.0. And oxygen, of course, if you divide by the smallest, gives us 1.0. So, so again, our ratio, I wouldn't round because it's not the same number of carbon and hydrogen. So technically it's C 3.5, H 3.0, O 1.0. But in this case, what we're going to need to do is multiply by 2 to get whole numbers. And so C7, H6, O2 is the best answer. And that's the empirical formula. Okay, and then finally, we might need to determine the molecular formula from the empirical formula. And remember again, the empirical formula gives us the smallest whole number ratio. The molecular formula is actually the actual molecule, the formula of the actual molecule. But since we know the empirical formula is the lowest ratio, the molecular formula will always be some multiple of the empirical formula because they have the same percent composition. So what we do is figure out what is the molecular weight, and we know the empirical weight, and so we can see how many multiples the molecule is. So let me show you an example of this. And actually, you can't do this unless you are told the molecular mass, the molar mass, or the molecular weight of the molecule in question. All right, so for example, suppose a compound has a molar mass of 60 grams per mole, and we just discovered that the empirical formula is CH2O. What is the molecular formula? Well, what we need to do again is see how many multiples of CH2O our molecule is. So if we find out the molecular weight of the empirical formula, 12 carbon plus 2 hydrogen plus 16 oxygen gives us a mass of 30.0. And then so 60.0, we can already see it, 60.0, we take the molecular weight of the molecule divided by the molecular weight of the empirical formula. And in this case, you will see that it's 2, which means our molecule is twice as big as the empirical formula, which means that we just multiply all the coefficient or the subscripts by 2. So the actual molecule is C2H4O2. So again, find the empirical mass, the mass of the empirical formula. You're given the mass of the molecular formula, and then just figure out how many multiples. Divide the bigger one by the smaller one, find out how many multiples you have, and then multiply each element by that number. Now we're going to get back to our stoichiometry that we started at the beginning of this chapter. Again, stoichiometry, and here it's a Greek word that means element measure. It is the calculations necessary to figure out how much reactant or product or one or the other is involved in chemical reaction. So it's the how to figure out, for example, if I'm in an industry and I want to know how much I need to have 100 kilograms of this particular product for my sales to work. So the question is, how much of my starting reactants do I need in order to get those 100 kilograms in the end? So it's relating the amounts of reactants to products. Or the other way around. I've got 10 kilograms of this over here. How much product can I make? What can I project that I can make? So it's based on a balanced chemical equation, and it is very fundamental, and so it's kind of a important thing to be able to do. And again, this will show up in other chapters throughout the semester. So if you're not quite with it, make sure and ask for help. All right, so let's actually look at an example how you use this every day, because this really is something, especially if you cook, you're really using the same idea. All right, so if we make a ham and cheese sandwich, let's say we use 2 slices of bread, 1 slice of cheese, and 3 slices of ham. So that just happens to be my recipe, and that makes 1 sandwich. So this is my ratio. For every 1 sandwich, I need 2 pieces of bread. For every 1 sandwich, I need 3 pieces of ham. For every 1 piece of cheese, I need 3 pieces of ham. These are all ratios in my equation. So what if I wanted to make 5.5 sandwiches? Grams. So if we take 28 grams of nitrogen plus, now each hydrogen atom weighs 1. There's 2 hydrogen atoms in a molecule, so that's 2 grams. There's 3 molecules, so that's 6 grams of hydrogen in total. And then if you add together NH3, we have 14 plus 3 is 17. There's 2 of them, so 2 times 17 is 34 grams. So you can actually see that the mass is conserved, and that's because you have the same number of atoms on each side. But the mole to mole ratio, the coefficients, have nothing to do with the mass ratio. So, suppose we wish to determine how many numbers of moles of NH3 we could produce if we have 4.8 moles of hydrogen. Because they're balanced, we can have a mole to mole ratio. So now we're coming up with new conversion factors. So what we can say is, actually we can take this ratio and we can say 1 mole of N2 is equivalent to 2 moles of NH3, or 1 mole of N2 is equivalent to 3 moles of H2, or 3 moles of H2 are equivalent to 2 moles of NH3. We can take any of those relationships and compare them to each other. So in this case, since we want to convert from H2 to NH3, then we use that 2 to 3 mole ratio. We call that the mole to mole ratio. So we start with 4.8 moles of H2. That's what we're given. Now we want to cancel out the moles of H2, so we put the 3 moles of H2 in the denominator, and we're trying to find out how many moles of NH3 we have, so that goes in the numerator, so the moles of H2 can cancel, and our answer will be in moles of NH3. And since we make 2 moles of NH3 for every 3 moles of H2, we have to multiply by 2, divide by 3, and we get 3.2 moles of NH3. So this is sort of the crux of the whole thing. You have to, if you're converting from one compound to another in a balanced ratio, you always have to multiply by the mole to mole ratio, multiply and divide. Now, of course, in the lab, we're mostly working with grams, and so moles aren't very useful. And so we need to be able to do the same thing by mass. So here's an example. How many grams of HCl are required to react with 5 grams of manganese 4 oxide according to this equation? So there's our balanced equation. So let's just refresh again what this balanced equation tells me. It tells me 4 moles of HCl react with 1 mole of MnO2 to give me 2 moles of water, 1 mole of MnCl2, and 1 mole of Cl2. And this is a balanced equation, and so this is true. So we can make a mole to mole ratio for any of these things. We can say 4 moles of HCl is equivalent to 1 mole of MnO2. They react in a 4-to-1 ratio. Or we could say the moles of HCl, 4 moles of HCl is equivalent to 2 moles of water. So we know that if we react 4 moles of HCl, we will make 2 moles of water. That's a mole to mole ratio. We can use any of these. It doesn't matter which side they're on. So in this case, however, again, just repeat, you cannot compare grams to grams in this balanced chemical equation. We only know how they're related in terms of moles. So before we can do anything else, we're going to have to convert grams to moles. So we know we have 5 grams of manganese 4 oxide. We first need to figure out how many moles that is. So once again, here's the reaction. 4 moles of HCl plus 1 mole of MnO2 gives me 2 moles of H2O plus 1 mole of MnCl2 plus Cl2, 1 mole of Cl2. In this case, they're giving us grams of MnO2, and we want to find grams of HCl. So we're only dealing with the 4 HCl to 1 MnO2 ratio. So the first thing we need to do is find out what we're given and convert this to moles. Again, because we only know grams, but the only way we can convert from one to the other is the mole to mole ratio. So the first thing we do is convert 5 grams of MnO2 to moles of MnO2, and we do that by using the molecular weight of MnO2, 86.9. Then we convert the moles of what what we're trying to find. So we know that the ratio, we know that we need 4 times as much HCl as we do MnO4 in terms of moles. And so if we convert 4 moles of HCl to 1 mole of MnO2. Now notice that our factor label method is working. So the grams of MnO2 have been canceled, and now the moles of MnO2 have been canceled. And if we did the calculation at this point, our answer would be in moles of HCl. But a lot of times what you need to know is the mass of the final product. So just be careful for what is being asked for. If the question said how many moles of HCl, then you'd be fine. But now we can convert moles of HCl to grams of HCl by using the molecular weight of HCl. So because the different compounds weigh different amounts, we have to first convert. We have to get out of the grams of the first one, and then we have to multiply back by the grams of the new compound. But the really important key is that center step where we figure out how many moles, and that's the one that students forget the most. You have to convert from moles of one to moles of the other. So that 4 moles of HCl to 1 mole of MnO2 is really, really important. So if you do the math, you'll find out that 5 grams of MnO2 need to react equally with 8.4 grams of HCl. So, 3-step process. Write what you're given, convert it to moles. If it's in grams, convert it to moles. Then convert moles of what you know to moles of what you want to know using the mole-to-mole ratios. And then finally convert the answer of your new compound into grams of that compound. The important point is that you can only make conversions from one substance to another by using the mole-to-mole ratio. So you're going to have to convert from grams to moles if you're not given moles. If you're given moles, then it's easy, but if you're given grams, you have to convert to moles. Since every compound has a different weight, you cannot compare weights directly. So, what mass of water is produced when 1.5 grams of glucose is metabolized in the body in the following reaction? C6H12O6 plus 6O2 gives us 6 CO2 plus 6 H2O. So, balanced chemical equation. Every 1 mole of glucose requires 6 moles of oxygen to give us 6 moles of carbon dioxide and 6 moles of H2O. All right, now we're not going to use all this data. We're starting with 1.5 grams of glucose, and we're looking for how much water is produced. So glucose and water are our main thing. And our mole-to-mole ratio there is 1 mole of glucose gives me 6 moles of water. So again, they can be on the same side. They can be on opposite sides. It doesn't matter. You just find the two that you're looking for and look at their coefficients. So again, our 3-step process, since we know grams, we're going to have to convert grams to moles. Use the molecular weight of glucose, which is 180 grams per 1 mole. That gives us 0.00833 moles of glucose. Again, you can do it all in one step. You don't have to do each step, but I'm showing you each step now. Take the answer from step 1, and now we have to multiply by 6 moles of H2O for every 1 mole of glucose, because we're going to produce 6 H2O for every 1 glucose. So that gives me 0.0500 moles of H2O, 6 times as much in terms of moles. Now, because water has a much different weight than glucose, we're going to take the moles of H2O, multiply it by the molecular weight of water, and we get 0.9 grams of H2O. So that's the process. Like I said, it's easier to do it in one motion in your calculator. Actually, if you do each step, that's fine. Keep all your significant figures in your calculator till you're done. Don't round it at each step or you'll get rounding errors. So what I do is either I write it all out and just do all the calculations at one time, or if I do one calculation, I leave my answer in my calculator, do the next calculation, so that you're not rounding with each step, because if you get a slightly different answer from someone else, if you're comparing your work, that's usually the reason why, because you've rounded differently. So here in this case, I might just say 1.50 times 1 times 6 times 18.0 divided by 180.0 divided by 1 divided by 1 gives me 0.9. So just do it all, and don't round too much is the main message of this. But then you just wait at the end, you can round to the correct number of significant figures. So use more digits until the end and then round. So in this case, because we started with 3 significant figures, our answer should also have 3 significant figures. So that's why it's 0.900. Also, a lot of students are kind of don't want to do this, but if you especially at the beginning, notice how I've written out grams of C6H12O6, and then in the next one I wrote moles of C6H12O6, grams of C6H12O6. I've written out the units along with my numbers because I was able to keep track of it. If you know what you're doing and you're pretty organized, that's fine, but you want to make sure that you're following. So notice in the first step, I've converted from grams to moles of glucose. Then in the second step, I've converted from moles of glucose to moles of water, And then in the third step, I've converted from moles of water to grams of water. And so if you're careful, keep track of what you're doing and what is canceled, and you'll be more successful. Now, I've written this little thing here. So grams of A. So if you're trying to go from A, something in the balanced chemical equation, to B, something else in the balanced chemical equation, start with the grams of A to get to moles of B. Start with grams of A to get to moles of A. You're going to have to use the molecular weight of A. In this case, you divide by the molecular weight. Then to get from moles of A to moles of B, you have to use the mole-to-mole ratio. Then finally, to go from moles of B to grams of B, you have to use the molecular weight of B, and that time you're multiplying by the molecular weight of B. Interesting though, don't get yourself too confused. If I gave you a problem and I gave you the moles of glucose instead of grams of glucose, well, you've already cut out the first step out of 3. So if this is a helpful guidance here, find out what you're starting with. If I said, if I gave you 0.8 moles of A, how many grams of water is that? Well, you're already starting with moles of A, so you skip that whole first step. You just go from moles of A to moles of B. So this is a nice little visual that you can follow. Where are you? If the question says how many moles of A gives you how many moles of B, you only have to do the middle step, but do as many steps as you need. And that's why I think using your units in your conversion factors can be really helpful.